Welcome to this presentation about using causal models for self-awareness in the SNOW project. My name is Willeke van Vught and I'm going to present the work my team and I did on this subject. I will mainly talk about the methods that we are investigating to discover causal relations and how to integrate those into our autonomous systems so that at the end we have to do less interventions. Well, enjoy and please reach out if you have any questions. SNOW is a project within TNO's Applied AI program for studying hybrid AI. So in a team of 15 to 20 scientists, we study hybrid AI in order to create safe autonomous systems that can operate in an open world. So our research focuses on three challenges: context awareness, user awareness, and self-awareness. And in this presentation, I show the work we did concerning the self-awareness challenge, where we want the autonomous system to be able to understand its own capabilities. So overall, we want to increase the self-awareness of the autonomous system. This entails on the one part assessing the task performance, but what we are mainly focusing on today is the reason why we observe certain changes in this task performance. So we are looking at generic methods to reason about what could be the root cause of over or underperformance of the system, using causal inferencing and using also knowledge about the requirement on our components, both functional and environmental requirements. We want to represent these causal relations in a knowledge graph. In this presentation, I'm first going to talk why causality is interesting for this work, how to discover causality in data, what methods are available, what data we have available for our autonomous system, and what are the assumptions involved in these methods. Well, what methods we are considering, reasoning about specific contexts and selecting intervention. Well, and then I'm going to sum up some future work. So first we should talk about what we mean when we say that there is a causal relation between two events. So generally speaking, we are talking about the influence of one event, which is the cause, on the production of another event, which is the effect. So at the right you see an example, and in this case, well, snowfall is the cause, and we want to look at the influence of this event on people slipping and falling. So there are many different interpretations of causality, but many mention that the cause is partially responsible for the effect, and the effect is partially dependent on the cause. So if we put it to the extreme, in a very deterministic interpretation of A is the cause of B, then B must always follow after A. So in this example I just presented you about snowfall, snowfall and falling of people would not be causally related because there are cases of snowfall and no falling people. So in addition, we also, most interpretations state that causes must precede their effects temporarily. So besides, we also have to note that in a large body of philosophical work on causality, it is debated that one can never observe the true causality, only a sequence of events. So let me start by explaining why we are investigating causal models instead of perhaps training machine learning predictors on KPIs of a search task. Well, actually, we would like to answer questions like, if I do action X here, what would be the effect of that on my performance? Or what is the cause of my bad performance currently? Well, and this we want to do to adapt the system and have less human interventions. And well, we notice that machine learning models can give an indication of performance, but do not by default output a suggestions of how to better manage your performance directly. Next, in addition, machine learning models have issues with generalizing to other environments or other tasks, making them less robust to open world scenarios. And in addition, especially neural networks are quite obfuscated black box models and not quite explainable to user or an operator. It's also not very straightforward to include expert knowledge into these models, so research is ongoing and improving on that, but it's not there yet. And it's also not straightforward to communicate or share knowledge with other autonomous systems using these models. So actually, causal models do have the promise of these properties, which is why we are investigating them in the SNOW project. So we are already using knowledge graphs in the project, and we are looking into how to apply these causal these two causal models and their effectiveness in the self-awareness case. So the gold standard to establish causality is by means of randomized control trials, where through randomization you try to rule out other factors that can influence the observed relationship, and you try to isolate the effect of the treatment or the intervention from unwanted co-occurring factors called confounders. Unfortunately, we cannot always perform these randomized control trials, although experimental data is a very strong indicator for causality. Sometimes it's just unethical or physically impossible. Often these randomized control trials are very costly to perform, and well, your test group might simply be limited in size. So other ways to do this is by means of simulation. Although the models used to simulate the data may be limited, reducing the confidence in the result. Observational studies are a possibility. These are more representative of the target population, but running the risk of combining confounding effects with treatment. Well, and actually for autonomous systems, we have a lot of observational data available. And in addition, we can do some intervention, although limited and somewhat costly. We are also limited in the number of sensors and actuators we have. Well, and thus action can, and so we are limited in the actions that can take place in the open world. So observational data for autonomous systems looks very promising, but one thing to take into account is that when you're using just observational data, there could be spurious correlations, which happen when two variables are correlated but do not share a causal relation. So in this case, confounders are not taken into account. So for example, what you show in this slide is an example about ice cream sales that are correlated with drownings. Well, obviously, these are not causally related, but have a confounder, namely sunny weather. So let's put it in the context of our autonomous system. So first, to identify these causal relations, we need to have a prediction and a theory or hypothesis to validate. So for our autonomous system, we have a lot of observational data, often time series data, and we can perform certain actions. So we want the system to hypothesize, given a current causal model, what could be the cause of a certain bad performance if encountered, and also try to validate its assumptions. So we are aiming here for the best causal model that explains the world, but the best is always potentially incorrect for our autonomous system because we are limited in our sensors and cannot fully observe the world. And also in actuators, and so, well, we cannot always validate our assumption in the best possible manner. So we are aiming for a causal model that allows the most effective adaptation, reducing the number of human interventions. Besides, at the low, you see that the nodes and the arrows we showed actually form a directed acyclic graph. This is, well, a presentation of a causal model where the nodes represent causal variables and the edges represent causal direction. And in addition, power or a time lag of causal effects can be modeled as attribute of these entities. So this slide shows how we incorporate causal models in our use case. So we first learn the initial causal model using observational data. Then by validating assumptions, we update the causal model in an online fashion. And then when during execution, bad performance is detected, we want to understand what causes bad performance by querying the causal model and eventually select actions that might mitigate that. So below here you see an example of the use case. So we have two rooms, one is well lit and one is dark. And the autonomous system has the task to search people and detect people in the rooms. And eventually we want to find this effect. So we want to find the relation that brightness affects detector performance. But if you turn on a pocket light, that might increase brightness. And in addition, also increase detector performance. So this is an example of the data we are working with. It's often time series data. And here I actually want to understand the effect of a illumination intervention, as you see it here, which is actually increasing the brightness for about 30 seconds on other variables like the brightness of the frame or contrast or image quality. So following our earlier example, we have two variables here, brightness and detector performance. And using observational data, we might find an initial causal model that brightness has a causal relation with detector performance. And to validate that, we would ideally like to change the distribution brightness and observe the change in distribution of the detector performance using interventional data. Well, using our autonomous system, well, we might turn on the forward light affecting the brightness. And ideally, we also want to, in a good randomized control trial fashion, use randomization to account for other confounding effects. So in this project, we want to identify these causal structures. So we want to identify the links between variables in the DAX under certain assumptions. So this is also called causal discovery or structure learning. And there are numerous approaches, but most either start out with a fully connected graph and then remove edges based on certain criteria. And some start out with an empty graph and then add edges. And generally, there are two approaches, constraint-based approaches, removing these edges based on conditional independence test or time ordering. And an example of this is the PC algorithm, which we use in this project. There are score and search-based approaches. They search for DAGs that best describe the statistical dependence relation in the data, such as, well, Bayesian networks or information theory-based approaches. And finally, there are hybrid approaches, of which we also will show an example later. So let us first talk about the assumption that underlie this discovery process. One main assumption is the causal Markov condition, and this assumes that all relevant probabilistic information that we can get from a system is contained in a direct causes of a certain node. So conditionally in the set of its direct causes, so a node in a graph, is independent of a variable which are not other direct causes or effects of that node. So this is what allows us to create this causal graph. Another assumption is the faithfulness assumption, and that states that relations or independencies in the data do not arise from coincidence, but from a causal structure. So if two variables are not correlated, they are really independent. And the third assumption is causal sufficiency, and this states that the measured variables include all the common causes. So this one is often violated in practice because, well, also for our autonomous system, we cannot measure the entire world, and therefore we are always restricted, and this weakens our strong causality. Other assumptions, for example, on data use are made by specific discovery methods. So for instance, in time series, an often made assumption is that it is stationary or separability, so that information about cause and effect is not fully contained in one single time series. So next to finding the causal structure, we are also interested in the causal effect of our time series, which is referred to as causal inferencing. So we have time series data available, and there are several methods from literature to deal with this. And one of the earliest methods is the Granger causality that establishes a causal link by determining how adding information of one time series improves the prediction of another time series. So there are various methods for this, such as the vector autoregression models. And the second condition for this method is that one time series always precedes the second time series. This method is not that suited for small data sets, but computationally quite light. And its main weakness is that it presents a very weak notion of causality prone to confounding effects. So we are also looking into other methods of causal inferencing, and I will go into a bit more detail later. And the first one is PCMCE, and this is based on a PC algorithm that we showed earlier in this presentation. This also has a momentary conditional independence test, which is explained later. And the second method is TCDF, which is a convolutional neural network approach, which we also show you in a bit. So let's first talk about PCMCE. This is a method that can do discovery and inferencing process, and it uses large time series data, which makes it interesting for us to investigate. It runs a time-based version of the PC algorithm, and not just looking at one time point, but also taking into account data points from a certain time window in the past. Well, this is the first step of the algorithm, but it might lead to false positives. so especially when taking a liberal time window or with highly interdependent or autocorrelated time series data. So therefore, the second step, the MCE, so the momentary conditional independence test, reduces the false positives by running conditional independence tests, including one of the parent nodes in the conditioning set. So there's a good open source implementation available. And the main thing to note is that the time window selection is very important in this method. So this is a general notion while working in causal models and time series data. So you need to specify what time range you are considering to establish relations. So for example, where you expect the effect. So this is challenging for autonomous system, and well, this might benefit from an adaptive approach. So the other method, the TCDF method, uses convolutional neural networks enhanced with the concept of attention. So attention is the concept which allows a neural network to learn when and where to focus on its input data or input signal to perform as best as possible during training. So as you see in the picture on the left, the input data is a set of time series. And the first step is then to train the actual neural network. And this is not a single network, but one per time series to be able to forecast the time series. So then for each network that was trained, an analysis step is performed and the attention of the specific neural network to determine to which time series the neural network has paid attention in order to forecast the time series. So after this attention interpretation step, the causal validation step is used in order to double check the causality of established links. And then the delay discovery step is used in order to determine the time lags for these causal relations. We use PCMCI as primary method to generate causal models in an autonomous system. After implementing and comparing both methods, both on our own datasets and through benchmark found in literature, we found that TCDF and PMCI show comparable results in terms of discovering the correct causal relations and hidden confounders. TCDF, however, is a bulkier method due to its multi-neural network-based approach and hence takes more compute resources and longer processing time. It does have some interesting features that are not in PMCI approach, such as being able to output a prediction of the various time series into the future. But in this research, we actually not using that features. So since we are in the end looking to generate new causal models on the fly on a robotic platform where resources are relatively scarce, we selected the PMCI method as a main method. And by designing these components in a modular way, we are always allowed to swap the methods as long as they generate causal graphs for any follow-up work. After investigating these methods, we are now implementing the PCMCE in our autonomous system. So as you see in all these pictures, we now have to establish an initial training set to generate these causal models for the system. So we operate our autonomous system in a large range of environmental conditions, so ranging from various lighting conditions, as you see on the left, like that impact the image brightness, image quality, and detector performance, for example, to also different variation in terrain that impacts spot movement, speed, drift, stability, as you see on the right. And we established a hypothesis for the resulting causal graph that modeled the effect of these variables on the key performance metrics, and run the various causal discovery and inference methods on the combined data set. Operating spot in these different environments results in a large time series data set. And we make a sliding window approach to generate causal models for every time range. So this is a quick process, and we can do this either for PCMCI or TCDF. This actually results in a data set of various graphs, which are labeled with a distribution of the sensor values under which the causal model was found. So in order to later to retrieve them. So the next step is a match and merge step, and we pruned a large set of causal graphs using a graphical embedding approach to determine the significant difference between the causal models by calculating the relevant distance in the vector space. And so eventually this results in a lower number of causal graphs that hold in the world in which the autonomous system operates. And this can be viewed as the observed rules of the world that our system has learned. And this process can be executed in an offline or online fashion in order to keep updating the system world models on the fly. Here we see an example of the generated causal model from data collection using a flashlight intervention. So on the left you see two example frames of the dataset, and well, in the middle you see the causal graph. We see some obvious relation occurring. So we see that contrast and brightness are highly positively correlated, and similarly lumen and brightness, for example. These variables each have a negative correlation, as you can see in the image, to image quality score, where actually it means that the lower score indicates a better image. We also see on the right of this image that the flashlight intervention is positively correlated with lumen, brightness, and contrast, and inversely with image quality. This is also what we expect to see from experience. Finally, we also see that the flashlight intervention is positively correlated to the image detection rate, although no causal relation is found with the confidence of these detections. Since in this example most effects are instant, the model fails to find the correct direction of every relation. This is still work in progress, and we apply the knowledge about system components and direction of data flow to mitigate that. Finally, on the right, you see the context labeling we use. This represents actually the distribution of sensor values under which the causal model was generated, and is used to identify the models in the operational phase. The end result of this whole process is a set of learned causal world models, which are labeled by context and form a foundation of the causal reasoning component. So to put it in context again, during operation a bad performance might be detected. So for example, when in a dark situation. And this then triggers the component to determine a best possible intervention in the current situation, which might be turning on a flashlight. And actually how the causal reasoning then works. So first the component will fetch the current state or context and retrieve the matching causal world model. Then traverse the model in order to find the most effective intervention. And lastly, update the internal knowledge base with this information in order for other system components like the planner to pick it up and use this information. So for example, actually turning on the flashlight for better performance. So we currently have discovered these relations, and we have these causal models. But we're actually still working on improving these models to make them more robust over different environments. We are recording additional data, especially for more terrain height variations. We are also modeling these interventions in the ontology, so that actually the intervention that we proposed by these causal models are implemented in the knowledge base of the system, and then eventually can be picked up by the planner component to actually plan these interventions in the action sequence. And then eventually at the end of the year, we want to do a field experiment and demonstration about this functionality. Thank you for watching this video about discovering causal models for self-awareness. And if you have any questions or remarks, don't hesitate to reach out.